Yeah, okay. Thank you. So I'm going to talk about my work on the joint learning of motion estimation and segmentation for cardiac MR image sequences. So we know that the cardiac MR can provide qualitative and quantitative information of the morphology and the function of the heart, which are crucial for assessing those cardiovascular diseases. And the cardiac motion estimation and segmentation are also two essential steps for the dynamic exploration of the cardiac function. So well, traditionally most approaches consider these two problems separately. However, we know that these two tasks are closely related, so learning the representation for one task should be helpful for the other one. So here on the right, we show an example of the image where we can simultaneously predict the segmentation and the motions. So that will be what we will be doing. All right, so in recent years, many approaches in deep learning have been proposed for the cardiac segmentation. Most of them employ fully convolutional neural networks that try to learn some useful features based on those manually annotated data that are normally those end-systolic, the SED, and end-systolic, the ES frames in a cardiac cycle. So this means that there are a large amount of data that haven't been explored. And on the other hand, for the cardiac motion estimation, traditional methods always extend the optical flow method or the image registration method for estimating the motions. And also some deep learning methods has also been proposed for the image registration, where they simulate some transformations as ground truth and then train an optical flow net to do the regression task. Well, in contrast, our network tries to do these two tasks simultaneously, where no motion ground truth is required and we only need some of the temporally sparse annotated data. So here is the proposed unified model, where it mainly consists of two branches. So the first one, so the above one, is an unsupervised motion estimation branch that is based on a Siamese style. We see the recurrent and spatial transformer networks. And the bottom one is a segmentation branch that is based on a fully convolutional neural network that is share the same feature encoders with the motion estimation branch. So I'm going to split these into two parts and introduce them in details. So the first is the unsupervised motion estimation branches. We know that the dense transformation fields before the frames are rarely available. Well, inspired by the success of spatial transformer network that can effectively encode the optical flow to describe motion. So here we propose to use a spatial transformer network to estimate the motion without supervision. So the task is to estimate a sequence of consecutive displacement field of the cardiac image sequence. Is the displacement field between the target frame, the IT, and the source frames, IT plus 1 or 2, IT plus the big T. And the output will be the displacement field, a 2D pixel-wise displacement field that describes the displacement along both X and Y dimensions. So here the network consists of mainly 4 components. So first is a feature encoder. Yeah, so it's a Siamese style feature encoders that extract the features from both the source frames and the target frames. So this network is adapted from VGG16net. And then we have a multi-skew concatenation layers that is motivated by the multi-level registration method, where we concatenate the features from these multi-levels and then upsample them to the full resolution. Well, this is followed by a recurrent, convolutional recurrent unit that can propagate the information along the temporal dimensions, because we are dealing with image sequences. And finally, after we have estimated the displacement field, we have a bilinear interpolation sampler that transforms the source frame to the target one. So this function here will be the transformations, where the gamma will be the bilinear interpolation. So to train the spatial network, we propose to minimize the pixel-wise mean squared error of the intensity changes of the target frames and these transformed frames. So this will be the intensity difference of these two frames. And to ensure the local smoothness, here we penalize the gradients of the flow map by using approximation to Huber losses proposed here. And similarly, to ensure to constrain the motion to behave smoothly, we also have a regularization term here. So to train the network, we use this loss function, where the t will be the sequence of the number of the sequence, and alpha beta trade-off parameter to trade off the image similarity error and such local and temporal smoothness. Yeah. So, well, since we know these two tasks are related, so here we propose to jointly train these two networks by combining them to share our same feature encoders. So we find that by coupling these two tasks, the features that learn from the motion estimations actually can facilitate the learning for the segmentations. So this can also be viewed as a weakly supervised segmentations because the segmentation network can utilize the features that has been explored from those unlabeled data by using those training the motion estimation branches. Well, specifically, we have two segmentation losses. First is standard categorical cross-entropy loss on the annotated data. And the second one is actually on the unannotated data. So what we do here is we first, so we transform the segmentations that doesn't have the ground truth to the frames that we have the ground truth. That is, will be the ED or the ES frames. And then we compute the categorical cross-entropy losses. So the FW will be the segmentation network plus the warp operations. So here the displacement field used will be the estimations from the motion estimation branch. So this can, it shows that it can make the estimations around boundaries to be as accurate as possible. So here is the composite loss function where we train the joint network, which consists of the image dissimilarity errors, some local smoothness, and also the segmentation losses. Yeah. Well, we performed experiments on the UK Bellbank data, which consists of 4,875 short-axis cardiac CNE MRI. Each scan consists of 50 frames, where manual annotations are only available on the ED and ES frames. So we split the data set into training, testing, and validations. Parameters were chosen based on the performance of the validations. Additionally, we also have the online data augmentations, including rotation, scaling, and translations. The number of sequences during training was set to be 10 in this case. So here we first evaluate the performance on segmentation, where we compare the joint model with the baseline method, that is segmentation only, which actually the network that removes the motion estimation branch, and it's also a work from our group. So we see that the joint model can outperform the baseline method in terms of the dice matrix significantly, with a p-value much smaller than 0.001. So this, in some sense, indicates the merits of the joint feature learnings. Similarly, we evaluate the performance of motion estimations. We compare that with the free-form deformation, the motion-only branches, and the joint model. So what we do here is we transform the ES segmentations to the ED frames by using the displacement field we estimated, and then compute the mean contour distance or the Hausdorff distance between these two segmentations. Yeah, so these results show the proposed deep learning method can outperform the traditional FFT methods, and, well, similarly, the joint model can have a better performance than the motion-only methods. Well, additionally, here we also show testing time that is performed on the 50 frames of a single slice in a cardiac cycle. So, yeah, we see that the deep learning method can offer a much faster speed in this case, which is also a benefit of the method. So to further validate the performance, we show some of the visualization results. So the figure A and B are the visualing results of the left ventricle and right ventricle boundaries along the temporal profiles. So here we warped the ED segmentations to the other time points by using estimated transformation fields. Similarly, for figure C is the change of the left ventricle volume across the cardiac cycle. That's also to warp the ED segmentation to other time points. Well, compared with the FFD, I think we can say that the proposed method can offers accurate, consistent, on smooth results. Yeah. So again, we show this example where we simultaneously predict the segmentations and motions. We overlay these segmentation motions on the of a cardiac cycle. So know that we actually estimate the dense transformation fields, but to have a better visualization, we just show up sparse representations here around myocardium. Yeah, so this looks good. And then, based on that work, we further investigate its applications or the capabilities of predicting such motions or segmentation directly from the undersampled MR data. So while we do this, we know the MR data acquisition speed is fundamentally limited due to some hardware constraints. So the most approaches consider undersample them in k-space and then reconstruct the images. Well, however, we know that in some cases, the perfect reconstruction may not be necessary as long as the images allow to extract those clinical relevant parameters. So it may be more efficient to directly obtain the final results from the undersampled data. So this motivates us to perform the estimations directly from undersampled MR data, bypassing the MR image reconstruction stage. And then the goal of this work is to make sure the predictions can be as accurate as possible with that from the fully sampled ones. So again, we adopt the network, what we described earlier, and then here we proposed a framework for the training on the right side. So this framework mainly consists of two subnetworks. So one is a fully sampled motion segmentation net. This is the blue ones, which is a well-trained motion segmentation net that mainly works as a supervision for the undersampled. And the second one is the green box that is for the undersampled data. This part will be what we want to train. So we know that there is a severe alias patterns on the undersampled MR data. So if we still do the same thing as what we did for the fully sampled ones, the network can hardly learn things. So to address these problems, here we propose to incorporate the fully sampled pairs. What we do here first, we propose to transform the fully sampled source frame to the fully sampled target frame by using the displacement field estimated directly from the undersampled images. Well, we find that such supervision is still a little bit weak or insufficient if the undersampled data is highly undersampled, like say 8 times or 6 times. So, and our goal is to push the result to be as close as to that from the fully sampled data. So here we additionally introduce an L delta term loss function here, where it tries to minimize the pixel-wise mean squared error between the displacement field that estimated from fully sampled and that from the undersampled. So additionally, we have a mask here which marks out the region of the interest. That will be the predictions of the segmentations. So this allows the arrows occurs only in the region of interest to be back-propagated to contribute to the learning and remove those noises. Well, similarly, we also have some of those supervision losses, where we use the ground truth if it's available, and if it's not, we use the prediction from the fully sampled data. Yeah, so then we train this network jointly with the L delta loss. This one will be image dissimilarity losses and the segmentation losses. Yeah, so we performed the experiments on the same data set. So here we simulated the undersampled data by using the golden angle radio undersampling patterns, where we examine the 3 times, 6 times, and 8 times. Here we see that compared with the FFD, the proposed method consistently outperform that. And as the acceleration factors increase, the performance have decreased, which is expected, but still very close to what we have obtained from the fully sampled images. And similarly, we have the evaluation on segmentations. It shows a consistent conclusion with the motions, but we evaluate the ejection fraction, which is a clinical parameter. That is the blood volume that pulled out of the left ventricle to the ratio of the total blood volumes. So here we see that even though the acceleration factor increases, the ejection fraction is still, the error is still very low, which could potentially enable some fast analysis of MR imaging. So we don't need to do image reconstruction, and we can directly predict these parameters like this. Yeah, our visualization results here. So here we show the results on the 8 times undersampling. So the first image will be the input image that looks very aliased. And then here we show the we compare the estimation from the undersampled and the fully sampled on the frames 15 and 20. Not sure if that's clear, but we see that it can give a good result, but though there are some small underestimations of the motions, like on frames of 20 or something. But in general, it looks pretty nice. Well, so to conclude, we have proposed a novel deep learning method for the joint motion estimation and segmentations, which consists of unsupervised motion estimation branches and a segmentation branch which share the same feature encoders. And this enables the effective feature learning via multitask training, and also shows the significant improvement of a baseline method. In addition, we also extend this method to predict these 2 problems directly from the undersampled cardiac MR data. So it shows that it's able to extract clinical relevant parameters directly from undersampled data while bypassing the usual image reconstruction stage. And such predictions obtained are also very close to that from the fully sampled data, so which, as I said, could potentially enable fast analysis for MR imaging. Well, that's it. Thank you.